terms of our contemporary climate, we're really moving into uncharted waters.
What are levels that we would deem to be dangerous human interference?
We underestimated how fast this could happen.
The actions we take today commit us and future generations to consequences.
It's very likely that the recent warming is outside of the range of at least the past 1,000 years.
And that's a bit alarming.
That's worrisome.
Climate change, perhaps the most pressing and complex scientific puzzle to confront mankind. During the past 4 decades, the National Science Foundation has invested billions of dollars unlocking the secrets of that puzzle. Join us as we examine what we've learned, what we know, what we don't, and what it could all mean for the future of our planet.
Dr. Kleen, how do we know that the global climate is changing?
We know from evidence. We have observations of the way the planet works. So we have thermometer records which give us temperatures of the soils, of the ocean waters. We have evidence from the ecosystems that the times when buds break in the spring are changing in response to warming, that the time when rivers freeze annually melt is changing in response to global warming. We have remote sensing observations from space. It's all consistent, all telling us the same thing, that we're living in a period of global climate change, in particular of warming. From every continent we're seeing this. Now what this means, of course, is we're working furiously on the scientific understanding, what's happening, why it's happening, and what it means for the future.
How much of this will happen, how bad this will be, depends on how much it warms. We already see a little warming, and we already see some things happening in response.
These are among the projections in the 4th assessment report of the IPCC, or the Intergovernmental Panel on Climate Change. It reflects the consensus of thousands of contributing scientists from around the world. Richard Alley is one of the authors of the 4th assessment report and one of the foremost experts on interactions of ice and climate. In this episode of To What Degree, Alley asks, how do we know? How do we know the climate is changing? How do we know what's causing it? And how do we know what may lie ahead?
Thermometers show that it's warming, including thermometers far from cities, thermometers placed in the ground, thermometers placed in the ocean, thermometers taken aloft on balloons, and thermometers looking down from space. Most of the ice on the planet is shrinking some. Seasonal snow and frozen ground and lake and river ice. We're seeing shrinkage of most of the glaciers on the planet, even where they're getting more snow. Where critters and plants live and when they do things in the year are moving towards colder places and towards colder seasons as they respond to the warming. Most of the indicators are saying the same thing, it's getting warmer. We still have weather. There are still cold days. Your neighbor can poke you in the ribs on a snowy morning and say, don't you love that global warming? Because we do still have weather. La Nina can cool the Pacific as the currents slosh around. If we have a big volcanic eruption, it will block the sun and make it colder for a little bit. To see climate, we have to look at a long enough average, and people usually use 30 years for that average. That smooths out over the weather. When we do that, all of the major measures of temperature show warming. This is the global average surface temperature since about 1850, which is as far back as we can get thermometer measurements to get a global average. And you see that it's warming. There's jumps and bumps and wiggles, but the general trend is up, and recently it's gone up a little faster. It's accelerated. Overall, since the beginning of the 20th century, the surface of the Earth is warmed by more than 1 degree Fahrenheit. Is this unprecedented? No. The climate is always changing. These are temperature data from an ice core showing the history of temperature in the Antarctic. And you see lots of ups and downs at temperature changes of many degrees over thousands of years. We want to know the long history of the climate, what happened thousands, even millions of years ago. But our thermometer records are very short, and we can get a global estimate for only 150 years. How do we find out what happened before that?
We have to turn to natural archives, what we call proxies, like these tree rings and corals and ice cores, and they can tell us about how the climate changed in the past.
Of particular interest is looking at, in a lot of these records, is looking at the warm periods, the interglacials, like we're in today. What were previous interglacials like? How much warmer or cooler were they? And particularly of the warmer intervals, what can we learn from those intervals about what's a warmer world like? How much warmer can it get? Can we determine the pace at which things changed when the Earth was warming and cooling?
You can't project into the future with climate change study unless you have a good understanding of what's going to happen at various breakpoints. Then just operating from the present into the future leaves us wide open for surprises that we might have been able to, stave off if we had a little better understanding of how the system operated in the past.
The layers of sediment in a lake basin, as long as they're relatively undisturbed, it's like reading a book. And with the oldest part of the story at the bottom, and we can read the story of what happened from looking at the various kinds of organic molecules and the sediments themselves. And so then we can reconstruct what that climate history was like in this spot. We can compare our record for the last 3.6 million years with cores taken from Antarctica and from other parts of the world.
Corals are extremely important in paleoclimate research. They fill an extremely important niche. And that is because corals are the only source of high-resolution, quality climate information from the deep tropics. What we do to generate these kinds of records is we obtain a core from a coral reef in the tropical Pacific, and a 50-year core is probably about 1 meter high. And we drill this core every single millimeter, and we run it through our instruments, and they're looking for very small changes in the chemistry of the coral skeleton. And we can measure these very precisely, thankfully, and we know how to translate these changes in chemistry to changes in climate.
We're able to develop calibrations that paleoceanographers and paleoclimatologists studying these fossils in deep sea sediments can use to reconstruct what the ocean's temperature was like tens of thousands of years ago.
Ice cores essentially represent a cylinder of ice that will be drilled out of an ice cap, an ice sheet, or a glacier.
And we take something called an ice core drill. It has a rotating set of teeth on the end of it, and it drills out a column of ice as much as 4 meters or about 12 feet long. And we bring that 4 meters up to the surface. We do all sorts of sampling on it.
Not only do we get the gases, the gaseous composition of the atmosphere, but we also can pick up dust fragments, various chemical species.
We can get the temperature of the air from which the snow fell. We can look layer by layer. How much dust was in 1970 versus 2,000 years ago? What was the composition of CO2 in the atmosphere in 1970 versus 2,000 years ago? So we can keep on going down the ice sheet as far back as we can go. In Greenland, that would be close to 200,000 years, we think. And in Antarctica, which has been an ice sheet much larger, been there for a long time. About 1.5 million years we can go back in time.
So by collecting various types of data, geologists have been able to put together a fairly continuous record of temperatures of ocean and atmosphere that extends back millions of years. But
with these proxy data, they're not precise thermometers. They're uncertain thermometers. They're fuzzy thermometers, if you will. And that means that there's a margin of uncertainty associated with reconstructing the past from these records. It turns out, however, that even taking that fuzziness into account, the uncertainties, the modern warming is so great that we were able to conclude that even with the uncertainty, it's very likely that the recent warming is outside of the range of at least the past 1,000 years.
so if the climate is warm before and the Earth is still here, what's the big deal? It's because the coming warming has the potential to impact society so enormously.
We've built a very sophisticated human society around a climate, a stable climate. If that climate shifts, are we going to be left behind? Are we going to be, one step behind our partner in the dance? I don't know.
We've built our society for the climate of the last 1,000 years. What we grow and eat, where we live, how we heat and cool, everything we do is suited for the modern climate. And if that climate shifts, it can change everything. A distinguished colleague of mine at Penn State, Michael Mann, has studied the history of temperature over the last 1,000 years. His result is often called the hockey stick.
What our study did was pull together all of the regional information and synthesize it into a single record so that we could actually talk about how warm the Earth was, or at least the northern hemisphere was overall, balancing out different regions that might have been very cold or very warm at any particular time. And when we bridged that information together and we synthesized that information into a single record, it was then that it became fairly clear in our study and other similar studies that the recent warming really is unusual in a long-term context, in part because unlike these past periods, like the Little Ice Age or the medieval warm period, the whole planet was essentially changing in lockstep. The entire surface of the Earth has been warming over the past century. That's the blade. Modern warming is the blade of the quote-unquote hockey stick, and then the handle, if you will, is the relatively moderate variations from century to century that existed before that.
So what's causing the modern warming? CO2, carbon dioxide. When we look at the history of the climate, what we find is that whenever CO2 has been high, it's been warm, and whenever CO2 has been low, it's been cold. And we can't explain the size of the temperature changes unless more CO2 makes it warmer. So what does CO2 have to do with temperature? It's simple physics, really. More CO2 makes it warmer through the greenhouse effect. The sun sends energy and heats the Earth sends back energy to space, and the CO2 gets in the way of some of that. That traps some of the heat here at the Earth and keeps us warmer than we would be. Without CO2 in the air, we'd send energy to space really easily. The surface of the Earth would be frozen, and we would be very unhappy, or we wouldn't be here. But as you turn up the CO2, adding more to the atmosphere, it traps more of that heat going up from the Earth, and so more CO2 makes it warmer. It's simple physics. CO2 is not the only greenhouse gas. Water vapor, methane, nitrous oxide, ozone, and others are also greenhouse gases. But CO2 looks like the main driver of the warming that's happening now. We know of no way to avoid the warming effect of CO2. More CO2 makes it warmer as surely as if you drop a pencil in the air, it falls down, not up. Here's the history of the concentration of CO2 in the atmosphere over the last 10,000 years. Look at the dramatic increase since the start of the Industrial Revolution. What's the source of this CO2? It's us. Burning fossil fuel for energy releases CO2. Think about your car. You put in 100 pounds of gasoline and you drive away. And as you burn it, you're adding oxygen from the air to make CO2, and you release 300 pounds of CO2 from your tailpipe. If it came out of the tailpipe the way waste came out of our transportation 100 years ago, as horse ploppies, it's a pound per mile driving down the road. We would cover every road in America an inch deep every year. And cars are just part of it. Whenever we burn fossil fuels, coal or oil or natural gas, for their energy, we release CO2 to the atmosphere. The CO2 is invisible to our eyes, but if we had special sensitive infrared goggles, we could see it coming out of the tailpipes and drifting like smoke across the landscape.
Well, it's quite clear that the contributions to the levels of greenhouse gases are related to the combustion of fossil fuels. And that's contributed by transportation, by energy production, by the destruction of natural forests, and all of that, the land use changes and the fossil fuel combustion are all driving greenhouse gases to levels we haven't seen for 1 million years.
What the ice cores have done is really allowed us to scale human impacts. We've burned a lot of fossil fuels. How much have we changed CO2? How much have we changed methane? How much have we changed nitrous oxide? And the ice cores tell us by generally about as much as the natural environment was able to do over the last 1 million years.
So how do we know that the rising CO2 is coming from burning of fossil fuels? How do we know it's not part of a natural cycle? Well, first of all, we have bookkeeping. We know how many trains full of coal and how many super tankers worth of oil we're burning, how much CO2 that makes. We see that CO2 in the air in the surface ocean. We've then gone and looked. Could any other source be doing this? What about volcanoes? Volcanoes are putting out 1 or 2% of the CO2 that we're putting out of our fossil fuel burning. They're really small. And then we've checked it. If you put CO2 out of a volcano, you're melting something, and that doesn't use oxygen. If you put CO2 out of burning coal, you're using up oxygen for the burning. And so a volcanic CO2 source, oxygen wouldn't change. A fossil fuel CO2 source, oxygen would be going down as the CO2 goes up. What's happening? Oxygen is going down as the CO2 goes up. It's burning. And there are other tracers that show that the burning is of something that was alive and has been dead for a long time. It's fossil fuels, it's us. We know from thermometers that it's getting warmer. We know that CO2 is rising from our fossil fuel burning. How do we know that the warming is caused by the rising CO2? Well, there's 3 pieces of the puzzle. It's physics and forcings and fingerprints. The physics is straightforward. More CO2 has a warming influence. We can't get around that. It's out there. The rising CO2 should cause warming. The forcings have been harder. We have to look, could anything else be causing the warming? So you put a satellite up and you watch the sun and you see if the sun's getting brighter, and it isn't. And could the heat be coming out of the ocean? Well, you watch the oceans and heat is going into the oceans. And you look at the volcanoes and anything else you can think of. We can't find any other forcing that is pushing us towards warmer. And then we look at the fingerprints. Suppose the satellites were wrong. Suppose the sun is getting brighter and the satellites missed it. If you turn up the sun, you warm everywhere up through the atmosphere. You warm at the surface, but you warm up in the upper stratosphere. If you turn up CO2, you hold the heat down here. It warms down here and it cools up there. And so sun, warm, warm, CO2, warm, cool. What's happening? Warm, cool. It's a CO2 fingerprint.
One fingerprint doesn't prove it. What else do the computer models that we use to make the projections predict? They predict the middle of continents should have warmed up more than the middle of oceans. That happened. They predict low latitude areas should warm up less than high latitudes. That happened. They predicted night should warm up more than day. That happened. We have 4 or 5 fingerprints that line up.
You can also look at what happened over time, and it's the CO2 fingerprint again. The observed pattern of warming cannot be explained by computer models if only natural causes of climate change are included. But when human causes of climate change are added, the computer models beautifully explain what happened.
What we find is that if we only put the natural factors in the models, volcanoes and the small changes in solar output that take place from one decade to the next, the models actually cool slightly in the late 20th century. It's only if we put the influence of humans, and in particular increased greenhouse gas concentrations in the models, that they are able to match that anomalous recent warming.
So, only the models that include what nature has done to the climate and what humans have done to the climate are able to recreate what actually happened. Where are we headed? What's in store for us? And are we really sure about all of this?
Probably one of the biggest fundamental questions of climate today is, what are levels that we would deem to be dangerous human interference, as the UN Framework Convention on Climate Change calls it? What are those levels? We're not to a point where we can answer that question yet, but unfortunately the harder we look at it, the lower the levels get, and that's worrisome.
To know how much warming we face, one thing that we need to know is how much warming you get from a given amount of CO2 that's put into the atmosphere.
Climatologists asked, if we doubled the concentration of CO2 in the atmosphere, or CO2 equivalent, how much effect would we see in the change in the temperature, the surface temperature of the Earth?
If the CO2 concentration in the atmosphere doubles, the global average temperature is projected to rise about 3 degrees Celsius, or a little more than 5 degrees Fahrenheit. But CO2 atmospheric concentrations may far more than double.
We don't study doubling of CO2 anymore. We study concentrations that are vastly higher than doubling of CO2, because we seem to be on this trajectory that will surpass 2 times CO2.
So how much will CO2 rise, say, over the next century? It depends on decisions we humans make on how much fossil fuel we burn over the next decades. Because fossil fuel use in the future is so uncertain, scientists have created a range of scenarios for how much CO2 we will emit based on how much fossil fuel we will burn. This graph shows the future temperature changes simulated by 23 state-of-the-art climate models for 3 of the scenarios for how much carbon dioxide we'll emit in the future. The wonderfully complex climate system involves some things that we really understand well and other things that we're a little bit uncertain about. The different climate models represent these uncertain parts in different ways, and so we end up with a range in the projections from the climate models for the different scenarios. In the scenario shown here with the smallest emissions of CO2, the warming by the end of the century is 1 to 3 degrees Celsius. The middle of the road scenario shows warming of 1.5 to 4.5 degrees Celsius, and the scenario with the greatest emissions of CO2 shows warming by the end of the century of 2.5 to 6.5 degrees Celsius. That 6.5 degrees is almost 12 degrees Fahrenheit. Uncertainty exists in projections about climate change, whether we like it or not. It comes from a lot of sources. It comes from the inherent unpredictability of humans and pieces of the climate system. It comes from the simplifications that have to be made to make this whole climate system fit into a computer. And it comes from uncertainties about key parameters that go into those computer models.
One of the key uncertainties is that it's very tricky to figure out how the El Niño phenomenon will respond to human influences on climate. Different models that are each credible in the way they treat the problem come to different conclusions. Will El Niños become bigger? Will they become more frequent? We don't know the answers to that. And until we know the answers to that, we're somewhat at a loss to make the kinds of regional climate change projections that we need to make.
But it's important not to confuse uncertainty with disagreement. The IPCC, the United Nations authoritative international group of scientists, is clear on the direction of change and the range of changes that we can expect. And as we continue to update our science and to learn more and to get better, we've crystallized this view without changing it. Our CO2 brings warming. Other authoritative groups, such as the United States National Academy of Sciences, also recognize the warming influence of our CO2. To test the validity of the climate models, we checked to see if they would have properly predicted the way climate has actually changed in the past. To do that, we run the models and we compare the model output to the actual paleoclimate records to see if they agree.
We sort of view ourselves as laying down the gauntlet, if you will. See, here, this is what we see in the real world. Do you see this in your climate model? Can you have climate change as fast in your model as we see in nature? Do you have the same pattern of change?
What we see in the tropical Pacific in these multiple coral records from the multiple sites is that this area has warmed more than the global average, and that it has also become more rainy over the last 50 years, appreciably. And so what that suggests going forward is that we can use that information to test climate models to see if they capture the magnitude and the sign of those trends correctly.
Because if a model can get the past right, particularly the big picture kind of changes, then it gives you a lot more confidence that it's getting the future right as well.
So the modelers use paleoclimate data to test and refine the models.
Taking the paleoclimate data, merging it with the models to literally try to force the models to better explain the past record, and in so doing, refine some of the parameters that characterize how the climate system operates, and therefore how the climate will change in the future if we continue to pump greenhouse gases into the atmosphere.
By and large, the greenhouse gases have very long lifetimes. Once they're emitted into the atmosphere, they stay there. Decades, centuries. Some of the carbon dioxide emitted by the first Model T is in this room still right now, and it'll be here 1,000 years from now, assuming the room is heated. That means that actions we take today commit us and future generations to consequences.
Have we waited too long to start to deal with this problem to avoid some of the impacts of climate change? And the paleo record unfortunately tells us yes, we have waited too long.
The full amount of warming from our greenhouse gases will not be realized for decades because the ocean is really big and it takes a long time to warm up. And while the ocean is warming, it's colder than the air, and some of the heat from the air is going into the ocean, and that keeps the air from warming quite as much as it otherwise would.
We are actually already committed to maybe 50 or 100 more years of warming, even if we could freeze greenhouse gas concentrations at their current rate, and that will require adaptation. Now, you can't adapt for changes that you don't know are coming, and that's why it's so important, for example, to refine our regional projections of climate change, and paleo data has a role in informing that.
The pattern of warming projected over the next decades is far from uniform over the surface of the globe, and the continent projected to have the most warming is North America. At least as important as temperature change are other likely impacts of climate change over the next century. More intense rainfall and flooding, more intense droughts in places and at times, increases in some extremes in weather, rising sea levels, lots of changes that matter to people.
Clearly something unusual is happening, and it's more or less what the models tell us should be happening as we increase the greenhouse gas concentrations. Those same models tell us that if we continue with the course that we're on and we follow business as usual over the next century, the changes ahead are going to be much greater than the changes we've witnessed so far.
So I think there's so much more to be understood and discovered. We often tend to think that we know all the answers, but it's not true.
We underestimated the climate system. We underestimated how fast this could happen. And so what it's teaching all of us as scientists is that, whoa, there's a lot we still need to learn in terms of how fast things can happen.
There is a small but finite probability, a non-negligible probability, that the changes that will take place in the future in response to our actions could be far greater than even our current models project. It has to do with some of these tipping points. We don't know exactly where they lie.
I know a lot of politicians are concerned that they fund a study thinking that will generate all the answers, and it simply generates more questions. But that's the way science works. We don't always come up with definitive answers, but hopefully, incrementally, we figure things out, and we, might be 2 steps forward, 1 step back, but eventually progress is made.
There's an immense amount that we don't know. We don't know what the climate will be in your backyard 30 years hence. We're working really hard to understand the regional implications of climate change, and those problems will be waiting for you to help us solve. We do know that when you come to help us solve those problems, that you'll be building on a very firm foundation. Our burning of fossil fuels does change the composition of the atmosphere, that does change the climate, and that does affect humans in ways that matter to me, to you, and to your children and grandchildren.